Let's continue the ZEUS training with section 5, the input bulk data cards for the Euler solver. So these are the bulk data cards we have, the MKParallel, the MKParallel, MKParam, trim FLT, viscous, and ST flow. Now all of the analyses such as flutter, trim, M-loads, G-loads, E-loads, GenGaf, and nonlinear flutter require the presence of the MKParallel bulk data card. And that is the association between the bulk data cards is shown in this chart. So the M-loads, E-loads, G-loads, and nonlinear flutter cards each refer to a flutter card. So for the transient time domain analysis, you are not performing a flutter analysis. However, these cards do refer to the flutter card to pick up the remaining cards. And then for a flutter analysis, you'll directly use the flutter card to define that flutter analysis. The flutter card refers to either a fix HATM, fix mock, or fix MDen. One of these three bulk data cards will then refer to the MKParallel card. Meanwhile, the trim and the GenGaf cards for trim and GenGaf subcases or modules refer directly to the MKParallel card. Now the MKParallel defines the reduced frequencies, and then it can refer to the trim FLT card, which then can refer to the viscous card for viscous analysis. And the MKParallel card, the ID number here, or the MKParallel refers to the MKParam, and then the MKParam and MKParallel cards can have the same ID card. The MKParam is for the parameters for the Euler solver module, and the MKParallel is parameters for the linearized Euler solver module. Now this is the MKParallel bulk data card. This defines the Mach number, the mean flow conditions, and the reduced frequencies. So ID MK is the unique identification number referred to by the flutter card or the trim or GenGaf bulk data cards. The Mach field is the Mach number. This is a real number. The ID param refers to the MKParam card and also optionally the MKParallel card. ID FLT refers to the trim flet card to define the mean flow conditions. The save field allows you to save or retrieve the GAFs computed by ZEUS. So when save is equal to save, then it saves the GAF data. For save equals acquire, then you retrieve the existing GAF data from a file, so you don't have to recompute that GAF data. You can use this if you want to rerun your flutter analysis. Save equals add will retrieve the existing GAF data and then add new reduced frequencies to it. And then if save is blank, you do not save the GAF data to a file, you just run the analysis. As a further option, save can be a character string, which is the name of a matrix. This matrix contains the mode shape matrix. This mode shape matrix was the mode shape matrix that was used to compute the saved GAF. And then based on this saved GAF and the corresponding mode matrix, the new GAF is computed by a least square approach. So for this case, if your structure model changes slightly, for example, you compute the GAFs for a full fuel condition, and then you want to rerun the flutter analysis with a half fuel condition, you can, with the full fuel condition, you save the GAFs onto a file, and then on the rerun, you have the new structure model with the half fuel mode shapes, but then you acquire the GAFs from the full fuel run, and then ZEUS will modify the GAFs based on the old and the new mode shapes, and then run the flutter analysis for you. So this can be used if the structure changes slightly, but obviously if you have a completely different structure model, it won't work as well. In that case, you would most likely need to run a new analysis. So the file name field is the name of the file where the GAFs are either saved or retrieved, and then print is a print flag which allows you to print out the unsteady aerodynamic pressure coefficients as well as the steady aerodynamic pressure coefficients of the mean flow. And then lastly, the open-ended input are the reduced frequency values. And the reduced frequency K is defined as K equals omega times ref c over 2 over V infinity, where omega is the frequency. Now the GAFs are only created if the MKArrow-Z card is referred to by the flutter, flupfast, GenGAF, or flupparam bulk data cards. For the transient response analysis, for example, M-loads, for the maneuver loads analysis, save is not used because no GAFs are created. And the entry MList in the flutter, flupfast, GenGAF, or flupparam can be used to remove modes from the GAF computation. Now for ZEUS, because the computational time for generating GAFs is proportional to the number of modes, reducing the modes can save computational time. However, the size of the actual matrix is NM, where NM is the number of modes in your structure solution. So when you exclude modes, those rows and columns associated with those modes will be filled with zeros. For the frequency domain analysis, acquiring the saved GAF matrices will skip the running of the Euler solver module for the GAF generation. Therefore, the flutter analysis will be very fast. And then this is the equation that ZEUS uses to create the new GAFs from the old GAFs. So phi old, here is our sample matrix name, which contains the modal matrix data for the old mode shape matrix, which is the mode shape matrix we used to generate the original GAFs. And then the new phi new, is the mode shape matrix that's imported by the assign FEM command. So this is the equation that ZEUS uses internally. Next we have the MKParam bulk data card, which defines parameters for the Euler solver module. ID param is a ID number referred to by the MKArrow-Z card. Method is a flag field to allow you to choose the flow solver. So method equals 0 is the full Euler run without any special options. Method equals 1 turns on preconditioning for the low Mach number cases. So if the Mach number specified in the MKArrow-Z card is less than 0.2, then we recommend turning on preconditioning. So this isn't done automatically, you must do this. And then lastly, method equals 3 turns on the linearized Euler solver option for frequency domain flutter analysis, trim analysis, or gust analysis. And this is what we recommend for ZEUS most often. You want to use the linearized Euler solver option. So in this case, the MKParallel card can be used to alter parameters for the linearized Euler solver. So in that case, the parameters in the MKParam will be used for the steady flow solution, and then parameters in the MKParallel will be used for the linearized Euler solver. TRM step is the number of time steps to compute the steady or the static aeroelastic solution, where the default is 100. Flut step is the number of time steps to compute the frequency domain generalized aerodynamic forces for flutter analysis. So this would be for method 0 or method 1. And the default is 201. Newton parameter is the number of sub-iterations per time step. So remember, this is where every Newton step we do the boundary layer coupling and overset mesh interpolation. And then n cycle is the number of Euler cycles within each sub-iteration. So if Newton is 4, which is the default, and n cycle is 2, which is the default, you'll go through 2 Euler cycles, and then after the second cycle, you'll do the boundary layer coupling and overset mesh interpolation for the Newton cycle, and then you'll go back and you'll do 2 more Euler cycles. And then after the second Euler cycle, you'll once again do the boundary layer coupling and the overset mesh interpolation. And you'll continue that for 4 cycles. And then after the 4 Newton cycles, then you'll perform the time step iteration, where that is the time step. If you're doing a time simulation, you'll step forward in time, and for the steady analysis, that's where you'll feed back to the structure, the steady static air elastic solution. You'll time step with the structure, and then move forward one more step. Next, the LVRSMOO is the residual smoothing flag for the Euler solver. So the default is 1. When it equals 1, we turn on the residual smoothing option. When it's 0, you turn off the residual smoothing option. PRNT-COV is the print convergence history flag. So when it's equal to 0, there's no printout. Equal to 1, you print out the convergence history of the last Euler cycle of the last subiteration for each time step. And then print convergence equals 2, which is the default. You print out the full convergence history. So every individual Euler cycle, you print out the convergence. The next row here, we have CFL, which is the CFL number, and the default is 7. Gamma is the specific heat ratio of the fluid, and of course the default is 1.4. Viz2 and Viz4 are the second and fourth order artificial dissipation parameters for the Euler solver, and the default is 1. And then TVD-COEF is the parameter involved in the TVD form of the pressure sensor of the JST scheme, and the default is 0. You can increase it up to a value just under 1 to smooth out the undesired zigzag pressure distribution that could occur on the lower surface of the wing at high angles of attack flow condition. But you want to be careful not to increase it too much, because that will smooth out the solution too much. And I believe we've, let's talk about the residual smoothing option here. The implicit variable coefficient residual smoothing scheme is incorporated in the Euler solver module that can extend the stability range of the Euler solver so that a larger CFL number can be used. So the residual smoothing option is always recommended, and that's why the default is on, unless the surface mesh has triangular panels, in which case ZEUS will turn off the residual smoothing. So without residual smoothing, the largest CFL number is generally less than 4. So for this reason, ZEUS will automatically reduce the CFL number to 4 if residual smoothing is off and the CFL number is larger than 4. In general, a larger CFL number results in faster solution convergence. Therefore, a larger CFL number is always desired. And then we've already talked about these other two terms. Next is the MKParallel card, which is similar to MKParam, except it's for the linearized Euler solver module. So the ID param, that's the identification number, which equals the identification number of the MKParam. K-expand, we can ignore that field. TRM step is the number of time steps to compute the linearized Euler solution. FLT step is not used. Newton is the number of Newton subiterations, and cycles the number of Euler cycles per subiteration. And then we have the residual smoothing option once again, and the CFD convergence history print flag. We have the CFL number and gamma, and Viz2 and Viz4. These are all the same as the MKParam. Next we have an epsilon parameter, so EPSC. This is a convergence control for the linearized Euler run, where the default is 0.0001. So in this case, when our residual drops by less than this amount, then the linearized Euler solver will terminate, even if you have not yet reached your TRM step number of steps. So if our default, we use 100 time steps, but then in our residual drops by a factor of 4 before we reach 100 time steps, then that particular K-mode pair will stop computation. So you can use this parameter to set a very large, if you would like, number of steps. But then if you only need, say, 4 orders of magnitude convergence, which that's our default, so that usually gives an adequate convergence. In that way, the K-mode pairs that converge quite quickly will not use up as much computation time. And then the TVD COEF, that's the same as the last one. And then lastly, the I lead, I trail, J left, J right, K bottom, and K top are no longer used and ignored. And our remarks are similar as before. We'll hit on remark 6 here. The linearized Euler solver solves the frequency domain unsteady aerodynamics for each reduced frequency and mode, K-mode pair at a time. The computation of each K-mode pair is independent of the other K-mode pairs. So for that reason, you can use the MPI for parallelization. So and you activate that using the MPI CPU executive control command. Next, we have the MK block. This allows you to assign different parameters for the Euler solver in different blocks of mesh. So we can assign different CFL, Viz2, or Viz4 parameters for each individual block. So if you have one individual block that is having difficulty converging, you can, for example, specify a lower CFL number or higher Viz2 and Viz4 parameters just for one block. So the ID MKBLK field is the identification number that's referred to by the entries CFL, Viz2, or Viz4 of the MKParam or MKParallel bulk data cards. And then the global value is the global value assigned to all blocks that are not overridden in the next inputs. So then for blocks that you want to override the global value, we have an open-ended input where we have ID block and value. So ID block is the identification number of the block T or block 1 card, and then value is the value of the CFL, Viz2, or Viz4 parameter. Next we have trim-FLT, which defines the mean flow condition. So ID FLT is the identification number. ID Viz is the identification number of a viscous bulk data card to define parameters for the inclusion of the boundary layer effects. So it can be 0 or blank to not have the boundary layer effects, or you can refer to the viscous card, which activates the boundary layer effects. Alpha is the angle of attack. Beta is the side slip angle in degrees, and then P rate, Q rate, and R rate are the non-dimensional roll, pitch, and yaw rates. The thermo field is not used. That's left over from Z arrow. And then the open-ended input label and value. Label is the label of the control surface defined in the AE-serv-Z, AES-link, PZT mode, or the grid force bulk data cards. And then value is the control surface deflection angle in degrees of that particular control surface. So this defines your mean flow condition. So the trim flood card is referred to by the MKArrow-Z card, as we said. And then if the ID Viz is 0, then the inviscid analysis is performed. These are the definitions of our non-dimensional roll rate, pitch rate, and yaw rate. And the label for the AE-serv-Z and AES-link, the units of the values in degrees. For the other options, the unit is defined by the user. Next, we have the viscous card to define the boundary layer parameters. So IVISC is the identification number referred to by the trim flat card. Next, we have the Reynolds. This should be REYINF, Reynolds infinity. So this is the Reynolds number based on the wing reference chord ref-C in the arrow-Z card, and the free stream conditions. So our length parameter and the Reynolds number is ref-C. The default here is 10 to the 6, so you'll probably want to change that to your Reynolds number. Tinf is the free stream temperature in kelvins. PRT is the turbulent Prandtl number, default of 0.9. RF is the relaxation factor for Carter's IBL coupling method, and the default is 0.1. And ICOUP is the viscous coupling method flag for ICOUP equal to 0. Edwards variable gain IBL coupling method is used, which is the default. And then for a value of 1, Carter's IBL coupling method is used. Now, usually Carter's method converges faster, however, it's less robust than Edwards' method. Therefore, we use Edwards as the default. And for a case with a large separation bubble, Edwards' method is recommended. Next, S0 is Sutherland law viscosity constant, and the default is 110. XKINT is the variable, and then let's see, so we have XKINT, XKINTH, and our remaining gain values. These are parameters used in the, let's see, XKINTs for the coupling method. XKINTH is the low-pass filter parameter, and then the gain BRK values are the nonlinear parameters that we saw a few sections back. AWK is the wake modeling parameters, along with WK-STRT and WK-STP. And then these are, the last three parameters are important. L transit is the transition point from the laminar to turbulent flow in percentage of chord, and the default is 20%. L body BL is the boundary layer option for the body. Now remember, the default is no boundary layer calculation on the body, but you can turn it on by specifying a value of 1 in L body BL, which turns on the boundary layer calculation on the body. Now if it's a negative integer, then its absolute value refers to a set 1 card in which a set of identification numbers of the body 7 bulk data card is listed. On these body 7s, the boundary layer calculation is turned off. And for all of the other body 7s, the boundary layer calculation is turned on. And then lastly, we have L wing BL, which functions the same as L body BL, except it's for the C arrow 7s. And the default for the C arrow 7s is to turn on the boundary layer calculation, but you can turn it off with a value of 0. Next, we have the ST flow to save or retrieve the steady flow solution. So ID bulk is the ID number, which matches either the flutter, mloads, eloads, gloads, trim, or nonlinear flutter case control command. And save is a character string, which can be either save, acquire, ACQU, save stop, or acquire stop. So for save, ZEUS will save the steady flow solution. For acquire, ZEUS will not compute the steady flow solution. It will retrieve the steady flow solution from the existing file listed in save file. For save stop or acquire stop, then ZEUS will terminate this current subcase after the steady flow computation. And for a acquire save and acquire save S, ZEUS will acquire the steady flow on the existing file and use that as the initial point, and then go ahead and recompute the steady flow and then save that new steady flow back on the file. And then acquire save S, it will stop the current subcase computation after the steady flow is computed and saved. Now save file is the binary save file for ZEUS to save and acquire the data. And then grid file and solution file are for you to view the steady flow solution. So grid file is an ASCII plot3D format used for plotting, and then solution file is the ASCII plot3D solution file for plotting. So these files aren't used for acquiring the old steady flow. It's just for the user to view the steady flow. So the first remark, if the ID number does not match the Flutter mloads, eloads, gloads, or non-linear Flutter case control command, then the ST flow card is inactive because it's not associated with a subcase. For Flutter, the steady flow solution is computed by the steady aerodynamic computation on the rigid configuration. For trim, the steady flow field is computed by the static aeroelastic computation on the flexible configuration for the thick cam trim variable. And then for mloads, eloads, gloads, trim, and nonlinear Flutter, the steady flow field solution is computed by the static aeroelastic computation on the flexible configuration prior to the time integration of the transient response. Here we describe how the plot3D file format is stored. So if you're interested in that, you can see there. However, it should be able to be read by any plotter that is able to plot the plot3D format.